Hi students, I hope all of you are completed the Coulomb's law problems. So in the up to the last class we completed the Coulomb's law concepts and all the models based on the Coulomb's law. So I think now you are confident about the Coulomb's law, so that you can solve any problem based on the Coulomb's law. So now from today onwards we are going to discuss about the electric field, so which is almost similar to that of gravitational field. And so let us see now this electric field and electric field strength. So electric field at any point is similar to that of gravitational field. Suppose here I am placing a charge Q. Now we know if it is another charge, let us say some small q is placed in the surroundings of this capital Q, this charge will experience a force, and even though these two are not in contact with each other, the force is there between those two charges, and so that is nothing but action at a distance. That means even though there is no physical contact between those two charges, one charge can influence the other charge. At the same time, this small q also can influence this capital Q here, so that there exists some interaction between them, even though they are far away from each other. And so that is nothing but we call it as action at a distance. And so such a similar action at a distance will be there in gravitation, and also it will be there in magnetism. And so in order to explain this action at a distance concept, we introduce the concept of this field. So we introduce the concept of this field whenever such an action at a distance is there, which is there in gravitation, and which is there in electrostatics here, and which is there similarly in magnetism. And so that is nothing but action at a distance. That means what actually happens is, so when this charge is placed at this point here, its influence will be there around this charge. Its influence will be felt around this charge in the space. If any other charge is placed in the surroundings, so that charge will experience the force due to this charge. So that means even though this charge is not there, if only this capital Q is present in the space, so its influence will be there in the space. So that influence, up to which that influence is felt, that region is nothing but we call electric field. And so if any other charge is placed in that field, that charge will experience a force due to this. And so that is the meaning of this electric field. So let us write the definition now. The electric field, the space around the charge, in which its influence is felt, the space around the charge in which its influence is felt, comma, if any other charge lies in that space, will experience a force due to this charge. Will experience a force due to that charge. Is called electric field. Is called electric field. So it is the meaning of this electric field. The space around the charge its influence is felt. And next, to measure this electric field, we use this word like electric field strength. So electric field strength, or you can also call it as electric field intensity. So electric field strength, or you can also call it as electric field strength. So now this is again similar to that of our gravitational field strength. So that means here the electric field strength at any point. Now suppose here this capital Q is fixed at this point, O let us consider. Now we are going to define the electric field strength at this point here, say at some point P. So in order to define the electric field strength at that point, we assume a unit positive test charge. We assume a positive test charge. So here remember that this is a test charge. Tester charge means generally we consider it as a very small, its magnitude is very small and it is a positive charge. That is the meaning of this positive tester charge. That means it is very small, tending to 0, so that it should not affect the field produced by this charge. So that is important importance of this tester charge here. The tester charge itself should not influence the field produced by the original charge. And so that means that is possible when the tester charge is too small. So if you are taking a too small charge, it doesn't influence the field produced by this charge much. And so that we can calculate the field produced by only this required charge here. The capital Q we can calculate here. So to define this electric field strength at this point P, we are placing a tester charge at that point. And so now this electric field strength at that point P is defined as the force acting per unit charge. That means F by Q naught, where F is the force, the electrostatic force acting on this Q naught. So that force per unit charge is nothing but we call electric field strength. So that is the definition of electric field strength. Write down the definition: electric field strength. So electric field strength at any point, electric field strength at any point is defined as force acting per unit charge, force acting per unit tester charge, force acting per unit tester charge placed at that point. Means if you want, you may mention in brackets like tester charge meaning a positive, it is always be considered as a positive charge only, positive charge and a very small charge tending to 0. That means more accurately to define this, so this is generally we write like this, and more accurately we can express like this. So more accurately this electric field can be expressed as limit F by Q naught, where this Q naught tends to 0. So that is the actual meaning of this actual expression for this electric field here. So we should consider this electric field same definition only. So same definition here, just I am taking it as a limit Q naught tends to 0. Q naught tends to 0 means that Q naught value should be very small. So that condition is also mentioned in this definition. So it is a more accurately we define like this. But in general we can also write general definition like this, F by Q naught, right? So it is a more accurately we express like this. This Q naught should be very small value, so that we can define electric field only due to this capital Q we can define there. Required charge we can define there. And next here you can mention the units. As you know the formula for this, you can mention the units. This F unit is Newton per Coulomb, and you can also express it as volt per meter, and later we will get a formula how the unit will be volt per meter. So from this formula you can remember it as Newton per Coulomb. That is the unit of this electric field. And next here the another point regarding this electric field law. This electric field is a vector quantity. The electric field is a vector quantity, and its direction is in the direction in which it is unit positive charge tends to move. That is more accurately we can define like this. The direction of electric field at any point. That means it is a vector quantity. I am representing it as a E. E is a vector, and its direction is at any point. The direction of electric field strength at any point is the direction in which this unit positive charge tends to move. So the unit positive charge tends to move means, let us consider, that means we are calculating field due to a positive charge, direction of field due to a positive charge at this point. The field due to this positive charge at this point we can define it as, what I am saying is the direction in which this positive charge tends to move, if it is free to move. So if that means we are placing this Q naught here, which is also a positive charge, and if it is placed at point P such that it is free to move, then what will happen is there is some repulsive force between these two. When there exists some repulsive force between those two, this charge will starts moving away from that Q, right? And so that means we can mention this electric field at this point will be along this direction. At any point, like suppose here if I consider another point here, then we place the Q0 here. Then again this Q0 will experience a repulsive force, and so then it moves along this direction here. So electric field at that point will be away from the charge. So like that, you can place anywhere. You can suppose if you consider here, then electric field direction will be like this. That means again the repulsive force will be there like this, so it tends to move like this. If you are considering a point here, so it will be like this. So from this what we can conclude is electric field due to a positive charge is away from the charge. There is a direction of electric field due to a positive charge. So electric field due to the positive charge at any point is away from the positive charge. So it is away from the positive charge, away from the positive charge. Here also it is away from. So like that, anywhere you may consider here. So the direction of electric field will be away from the positive charge. And so similarly, if you consider due to the negative charge. So if I consider due to the negative charge here, I am taking it as a minus Q. And so then here suppose we need to find the electric field direction. Electric field direction due to this negative charge. Then as I said, the direction of electric field at any point is in the direction in which the unit positive charge tends to move. That means here if we release a particle Q0 here, then there is some attractive force acting on this. And so because of this attractive force, it starts moving towards this direction. And so that we can say electric field will be in this direction. So like that anywhere you may place here. If you are placing here, then it will come towards that. And if you are placing here, then it will move like this. So anywhere you may place here, or you may place like this, then it will move like this. So that means from this what we can conclude is the direction of electric field due to the negative charge is towards the charge. So that is the direction of electric field. As only the two types of charges are there, now we can get these conclusions here. Electric field due to positive charges towards the positive charge is away from the charge at any point, and electric field due to the negative charges towards the charge. So that we should remember. That is the direction of this electric field now. So that means after that you may mention that point. It is a vector quantity. The direction of electric field due to a positive charge is away from the charge. You may mention this diagram here. So that electric field at any point will be away from this charge. And direction of electric field due to a negative charge is towards the charge. So if I consider a negative charge like this, then draw this diagram for this. So then electric field will be towards the charge. Then for this, the electric field will be like this. And here the electric field will be like this. So electric field will be to the negative charge, it will be towards the charge. And next here, from the definition, we can mention one point here, which will be used later. Like suppose according to the definition, we mention like electric field strength is mentioned as F by Q0. So from this, what we can write is, suppose I am writing this equation like this. F is equal to E into Q0 we can write. That means in general, what we can write is, so in general, I can express it as F bar is equal to E bar into Q. That means now this expression gives force acting on a charge Q when it is placed in an electric field of intensity E. This expression gives the force acting on a charged particle Q when it is lying in the electric field of E, strength E, electric field strength E. And that is the vector relation. So that means if you are using this vector relation, we know whenever you are using the vector relations, whenever charges are there in that formula, charge must be substituted along with the sign if you are using vector formula. And so that means according if charge is positive, you will get this as positive. That means both the vectors are the same sign, and so that we can say that E bar and F bar will be in the same direction. And if the charge is negative, then here you will get a negative sign, we need to substitute here, and so here you will get minus sign, and so F bar and E bar are opposite each other. That means, so we can conclude here, if suppose a charge is placed at this point where electric field is along this direction here, and if it is a positive charge, then force acting on the charge in this electric field will be in the direction of electric field, and the force acting on a negatively charged particle is, suppose it is minus q, then it will be opposite to the direction of electric field. So this is very important point. So note down that when a charged particle q is present in the electric field of intensity E, the force acting on the particle is given by, when a charged particle of charge q is placed in an electric field of length E, the force acting on the particle is given by F is equal to, or F bar is equal to E bar into Q. The direction of this force is, in the direction of electric field. The direction of this force is in the direction of electric field if charge is positive, and it is opposite to the direction of electric field if the charge is negative, and it is opposite to the direction of electric field if the charge is negative. And mention these two diagrams also so that you can understand that easily. And next let us see electric field due to a point charge. Electric field due to a point charge. So you consider a point charge Q, capital Q is placed at the point O, and we need to find the electric field at the point P, which is at a distance r from this. So that is our requirement here. A point charge Q, capital Q, a positive charge, is placed at the point O or fixed at the point O. We need to find electric field at the point P at a distance r from this point charge. And so for this, we assume a unit test charge is placed at that point. So we assume a unit test charge is placed at that point. So now, according to Coulomb's law, let us write the force acting on this Q0. So by Coulomb's law, so force acting on Q0 can be expressed as F is equal to 1 by 4 pi epsilon naught capital Q into Q0 by R square. So it is the force experienced by a unit positive charge Q0. And so now from this, according to our definition, so from this I am writing this as F by Q0 is equal to, just I am writing this Q0 this side. And so from this you may write this as 1 by 4 pi epsilon naught into Q by R square. So that is the expression for this F by Q0 value. But according to our definition of electric field strength, this F by Q0 is nothing but our electric field strength. And so, but E is equal to F by Q0. Therefore, electric field strength we can write it as 1 by 4 pi epsilon naught into Q by R square. So that is the expression for electric field strength due to a point charge at a distance r from this. And the direction, as we discussed previously, if it is positive charge, it is away from the charge. So here the direction of the field will be like this, away from the charge you will get. And if it is a negative charge, it will be towards the charge. So direction we can decide depending on the nature of this capital Q. And so then here this is the expression for this. And so then here you can observe that the electric field strength due to a positive point charge is inversely proportional to this r square. It is inversely proportional to the r square, we can mention here due to a point charge. And so if I draw the graph between electric field strength due to a point charge and r, then you will get a graph like this. So that is a variation of electric field strength with the point charge here, if you are moving away from the charge. And next, similarly here, this is expression for electric field strength in air or vacuum. So as we discussed in the Coulomb's law, if this charge is present in any dielectric medium, then we need to write this epsilon naught. Instead of epsilon naught, we need to write this epsilon. So I will write here in any medium that is dielectric medium. So I can write this as A medium is equal to 1 by 4 pi K epsilon naught. So directly I am writing here actually we need to write this epsilon. Instead of epsilon I am writing it as K epsilon naught into Q by R square. So this is expression in this dielectric medium here. So where this K is equal to epsilon by epsilon naught, dielectric constant. So it is a dielectric constant of that given medium. So that is expression for electric field strength due to a point charge in any dielectric medium, and that is the above expression which is in maximum level. So that is electric field due to a point charge there. Electric field intensity due to a point charge. So just we are writing Coulomb's law expression, force between them, and from that Coulomb's law just we are defining it as F by Q naught. So that F by Q naught gives us field strength. So next here I am going to define about this null point. Null point or the neutral point. So here simply this null point or the neutral point is, by the name it indicates that the electric field at that point should be zero. The field strength at that point should be, resultant field strength at that point should be zero. That means when two or more fields are acting in the space, so at some point there may be a chance of getting that neutral point. That is, when two or more fields are acting such that the resultant at that point is becoming zero, then that point is nothing but we call it as a neutral point. So simply write the definition of null point or the neutral point. The point where a resultant electric field is zero. The point where the resultant electric field is zero is called a null point or neutral point. So let us take the example of this when two light charges are there here, Q1 and Q2, and both are positive charges only. That I am taking it as case 1. So let us discuss the simple case now. When two charges are separated by certain distance d, so d is the separation between them. So then Q1 and Q2 are separated by distance d, and both are light charges I am taking. And so now first let us consider the region where there is a chance of getting the neutral point, either in between the charges, or on the left side of this Q1 or on the right side of this Q2. So let us verify first. So for example, here I am taking a point here. Simply there is a chance of getting neutral point when the field due to Q1 and Q2 are opposite in direction. So then there may be a chance when they are opposite in direction. If they are in the same direction, the field due to Q1 and Q2 are in same direction, definitely you can conclude that there is no chance of getting the neutral point in that region. So then here I am taking a point on left side of this Q1. So then here electric field due to this charge E1 will be along this direction, and electric field due to Q2 will be along this same direction, because that is also a positive charge. Electric field due to positive charge is away from the charge. So now both Q1 and both E1 and E2 are in same direction. That means both the charges are producing the electric field at this point in the same direction. And so that here there is no chance of getting the neutral point here. So neutral point is not possible. Then next let us consider case here. And so then similarly if you consider this Q1 and Q2. So then electric field due to this Q1 is away from the positive charge, so it will be now towards right. And electric field due to this Q2 is also towards right. That is also away from the charge. And so that now the electric field due to both the charges will be away from the charge. So that means again both are in same direction. And so then here also there is no chance of getting the neutral point there. So now let us take in between the charges. Suppose here I am taking a point here. Now electric field due to this Q1, it is positive charge, so away from the charge. So along this direction you will get. And electric field due to this Q2. So now it is away from the charge, so you will get along this direction. So now you can observe that Q1 and the electric field due to charges Q1 and Q2 are in opposite in direction. So opposite in direction means then there is a chance of getting the neutral point here. If their strengths are also equal, that means if magnitude of E1 is equal to magnitude of E2, then there is a chance of getting a neutral point here. So I am assuming that at a distance x from this Q1, their strengths are equal, so that the neutral point is obtained at their positions there. And so now there I am just equating the magnitudes now. E1 is equal to E2. So this is the neutral point I am assuming here. So then E1 means you can write this as 1 by 4 pi epsilon naught Q1 by x square. This is equal to 1 by 4 pi epsilon naught Q2 by x d minus x whole square. The distance from Q2. The distance from Q2 will be d minus x whole square. This distance. And now let us simplify this. So I am writing the equation as d minus x by x whole square is equal to Q2 by Q1. Just by rearranging the term. This constant 1 by 4 by epsilon naught will be cancelled. This d minus x I am writing here, so that this Q1 goes to here. So I can write this as d by x minus 1 is equal to under root Q2 by Q1. And therefore this is d by x is equal to under root Q2 by Q1 plus 1. And from this I can write this x is equal to d by under root Q2 by Q1 plus 1. So this is the expression for this distance of the neutral point, and this x is we are measuring from Q1. So that is also important here. So sometimes they ask the distance from Q2 in the question. So you should read the question carefully, whether they are asking from Q1 or they are asking from Q2. So that is we are calculating x is from Q1 now. So if the question is about Q2, they are asking distance from Q2, then d minus x you should answer there. So then that is, and here this root is only for this Q1 and Q2. So that is the expression for this distance of neutral points from Q1 when the two charges are positive charges. So it is the example now. And now let us consider the second case now. That means I am taking now unlike charges. I am taking that two charges or unlike charges. So this is Q1 and this is Q2. And suppose this is positive charge and this is a negative charge. And I am assuming the case like mod of this Q2 is less than that of mod of Q1. That means Q2 magnitude is small when compared to that of Q1. That is the case we are considering here. And distance between them is again same, d. D is the distance between those two charges. And so now let us write the expression. Now first of all, similar to our previous calculation, first let us identify the region in which there is a chance of getting the neutral point, like either in between the charges or outside the charges. As the previous case, when the like charges are present, we are getting the neutral point as in between the charges. So let us check now in between the charges now. Suppose I am taking a point here. Now electric field due to this Q1 is away from the charge, so then it is along this direction, and electric field due to this Q2 is, that is now negative charge. The electric field due to negative charge is towards the charge, so then E2 will also be in the same direction, right? And so that now both are in same direction, so there is no chance of getting the neutral point in between the charges, right? Because we should add them, E1 plus E2, we should write that net field means. And now suppose I am taking this side here. Outside the charges, on the left side of this Q1 I am considering now. The electric field due to this Q1 is away from the charge like this because it is positive charge, and electric field due to this negative charge is towards the charge. So then E2 will be along this direction. So they are in opposite direction. So there is a chance of getting the neutral point here. Now similarly let us check here. This side. Now here this E2 is away from the Q1 is away from the charge because it is positive, and electric field due to Q2 is towards the charge. So then there also the fields are opposite in directions. As according to our discussion, there is a chance of getting the neutral point because the fields are opposite to each other. And so now here we should conclude whether this side neutral point is possible or this side neutral point is possible or both sides it is possible. So that simply in that case we need to check about this tens here, the magnitudes of the charges. So only again I am saying only we should consider the magnitudes of the charges. Don't consider the sign when you are when you are finalizing the side on which that neutral point is formed. So only we need to check the magnitude. So neutral point will be always closer to the side having lesser magnitude of the charge. So here Q2 is less, so always that means neutral point will be formed this side. Because simply the reason, the explanation for that is, if you are taking this side, and we already mentioned in the previous formula, like electric field to a point charge, E is inversely proportional to, E is proportional to Q by R square. And so for this Q1 is large when compared to Q2, and this point is closer to that of Q1. Closer to this point charge Q1 when compared to that of Q2, and so automatically this Q1 will produces the strong field when compared to that of Q2, and so that here for any point on this side always you will get Q1 E1 is greater than that of E2 you will get. So that means there is no chance of getting the equal magnitudes there, and so that even though fields are opposite in direction, the neutral point is not possible this side. So that is the way, that is simply you can remember like this. So that simply you can remember it as when the charges are unlike charges, the neutral point will be outside the charge, and that too towards the charge having lesser magnitude of the charge. So towards the charge having lesser magnitude of the charge, the neutral point will be formed. And so now here we are taking Q2 is large, small here, so neutral point will be formed on this side. And so now let us proceed similar to that of our previous calculation, previous case, first case. That means here also I am taking this distance as x1 from this. X is measured from the Q1 I am taking here. That means distance of the neutral point from Q1 only I am calculating. So again there the electric field E1 should be equal to E2. The electric field due to this first charge in Q1 we can write as 1 by 4 pi epsilon naught Q1 by x square, that is equal to 1 by 4 pi epsilon naught Q2 by, now distance from Q2 we need to write this distance. So that distance we can write as x minus d whole square. So it is the distance there, and therefore I can write this as, again simplify this. So x minus d by x whole square is equal to, again we can write this as Q2 by Q1. So I can write this as 1 minus d by x is equal to root q2 by q1, or we can write this as d minus x, and d by x is equal to 1 minus under root of q2 by q1, and therefore this is x is equal to d by 1 minus under root of q2 by q1 you can write. So this is again distance of neutral point from q1. So measured from the q1. So q2 means x minus d you need to write distance from q2 means. So that is a way of calculating the neutral point there. So just we need to identify whether the fields are in same direction or in opposite direction in that particular regions. And so then when they are opposite direction, there is a chance of getting the neutral point, so we can equate them. And these are the general two cases there. When the charges are like charges, now we can conclude that neutral point may be there in between the two charges. When the charges are unlike charges, the neutral point will be there outside the charges and towards the charge having lesser magnitude of the charge. And that is the expression now. Like similar to that of our force, Coulomb force, this electric field strength also obeys the principle of superposition. So actually here we are writing E1 plus C2 is equal to 0 or modulus of E1 is equal to modulus of E2 means that is nothing but principle of superposition. As we discussed in force, Coulomb force, principle of superposition here is nothing but when combination of charges are there, distribution of point charges are there, the intensity of electric field at any point is a vector sum of field due to individual charges. So that means when combination of charges are there, so principle of superposition. So when combination of charges are there, like Q1 and Q2, Q3, like Q4, like different charges are there here. Now electric field at any point, suppose here we need to find the electric field here. So then electric field at any point is a vector sum of field due to individual charges. That means at this point we find the field due to Q1 both in magnitude and direction. Similarly we find the field due to Q2, Q3 and Q4 and we add them vectorically. And so then that is nothing but that gives the resultant electric field strength at this point here. So simply we mention that according to principle of superposition, the resultant electric field at any point is a vector sum of field due to individual charges. Field due to individual charges. So like here I may mention the directions like this is E1, E2, E3 and this is E4. Then the resultant electric field at this point I can write as E1 bar plus E2 bar plus E3 bar plus E4 bar. If more number of charges are there, you can add them and so on. If more number of charges are there in the distribution. So like that we find the field strength due to individual charges and we add them so that to get the resultant field at that point. And we solved a lot of problems based on the principle of superposition, Coulomb's law. Now such a similar problems will be there in calculation of this intensity of electric field also. So one example I will explain here. So remaining you can solve previous similar to that of previous Coulomb's law problems. So A, B, C, D. Now in a sphere of side D, this is a sphere of side D. You can write a common problem here. Find magnitude of electric field strength at point A in the following configurations or in following cases. So now here three charges. Here it is Q and here also it is Q and here another Q is there. So now the first question, this one, I will explain this one, remaining you can solve. So three charges are there at the corners of a square. Then find the electric field strength at the fourth corner. That means that is our point A here according to the problem. And now simply similar to that of our principle of superposition, we find the electric field due to B, the electric field due to C at point A and electric field due to D at point A. And we add them rhetorically. And actually as we solved the force problems, then you can easily write this, you can easily solve this type of problems also, field problems also. If you remember the force expression finally there, so you can directly define this as F by Q. That gives electric field strength at that point. If we already solved some problems based on this. So then if you already solved those problems, simply you can write this as F by Q at that point you can define. That gives a field at that point. So let us solve our procedure according to our principle of superposition here. So the electric field due to this B that I am taking as E1. So that is along this direction, and electric field due to this D that I am taking as E2, and electric field due to this C that I am taking as E3. So now let us write first their strengths. Electric field due to E1, E2 and E3 let us write here. So E1 is equal to E2, so that I can write as KQ by D square. That is a point charge form. Electric field strength to a point charge. And next E2, E3 expression you can write here. So KQ by this distance will be now root 2D. So I can write this as root 2 into D. And so whole square this is. And so I can express this as E1 by 2 because KQ by D square is E1. So E1 by 2 you can write. And so first we find the resultant of E1 and E2. So let us find the resultant of E1 and E2. So I can write this as, I am taking this as E dash. So this E dash is nothing but E1 square plus E2 square. Just a parallelogram, both are perpendicular to each other. So that 2PQ cos theta term will be 0. And so this is nothing but I can write this as root T E1 we can write it because these two are equal. So instead of E2 also you can write E1. So that gives us root 2 E1. And next let us write this. Now this E dash will be in the direction of this E3. By using the vector properties you can easily write that. We already know that, we solved some previous problems also. When these two vectors are equal, the resultant of those vectors will bisect the angle between them. And so that this will be this E dash will be in the direction of E3 you can write. So now I am writing that a resultant of E dash and E3. So that is nothing but our net electric field at that point. So I can write this as E dash plus E3 we can write. So E dash is equal to root 2 E1 plus E3 is nothing but E1 by 2. So that you can take E1 take common and you can substitute that E1 value. KQ by D square into 2 root 2 plus 1 by 2. So that will be the electric field strength due to those three charges at the corner A. So like that you can solve, we can take the mini configuration and you can solve those problems there. We find the electric field strength due to each charge and both in magnitude and direction, and we find the resultant of all those fields there, so that you will get the net field at that point. So now I will give some configurations here and you can solve those problems there based on this concept here, because you solved already some force problems. So then you can easily solve now the field problems also. So the same question, let us note that another same question. So I am moving this diagram now. Now the second example or second problem in that. So again I am taking the square configuration. Now the charges are taken here at the four corners of the square, like a Q, and this is Q, and this is also Q, and this is our point A. So as we mentioned, field strength at point A in every configuration we need to find. In every case we need to find here. So suppose that this is point B, C, D. This is E, and this is square of side B here. So at this point we need to find here. That means when four charges are there at the corners of a square, we need to find the electric field strength at the center. And in the square configuration only, you may change the charges. Like suppose I am taking this as negative charge minus Q plus Q, and this is minus Q and plus Q. So just I am changing the configurations, charge values, and again we need to find this also a square only, and we need to find a point D at point A. So the next problem I will draw here. Then this is again I am taking a square. Now like I am taking these two charges as negative and these two charges as positive, and electric field strength at point A we need to find here. And next let us take this triangular configuration. So this is an equivalent triangle. Let us consider now. Here this is B, this is C, and this is the point A. So here charges are there, two charges are there at the points B and C. So at 2 point charges are there at B and C, we need to find electric field strength at the point A, where there is no charge. At A, that configuration for the fifth one, there is no charge at point A. And so next let us draw this. So I am taking the same configuration here. This is Q and this is minus Q, let us consider. Now this is the point A. This is suppose say B and C. That means just I am taking a negative charge here in the same similar to the above fifth one. And next let us consider that this is also an equivalent triangle only. So now let us consider this equivalent triangle. Three charges are there. So here the three charges are there, Q, Q and Q. Field at the centroid. So the direction of the field at the centroid. Next is in the same configuration I am taking this as a negative charge. Again we need to find this field at the center. This is our point A and this is also an equivalent triangle. So this is also equivalent triangle. Next I can draw this another configuration here. This is 9th one. A regular hexagon I am considering now. So in this regular hexagon, this is Q, Q, and this is also Q, Now suppose this is the point A here. Here there is no charge again. These are the corners A, B, C, D, E, F. And again let us take this regular hexagon of side D. So at point A again we need to find that electric field strength. Now next I am taking this problem like at the same regular hexagon, all charges are present at the 6 charges are present at the 6 vertex. Now we need to find at the center. So at this point now we need to find, and this is also a regular hexagon so that any side will be equal to D. And the next one I am taking in this so here for example these are charges are like this, Q, Q, and this is also Q. Now it is minus Q, and this is also minus Q. Now we need to find this field at the center, and this is also regular hexagon of side D. And try to solve these problems based on this electric field concept, principle of superposition. So as you solved already this Coulomb's law based on the Coulomb's law, so here also same procedure. Just only instead of writing the force formula, we need to write this electric field formula. Just kq by r square formula we need to write here. Point charge formula, another simple applications will be there. Like suppose here if I consider a complete ring, the electric field strength at the center of this complete ring will be 0, because in force calculation we already did this. When the charge is distributed throughout this ring, then force acting on the charged particle placed at the center will be 0. But whereas now the question is, here a small gap is there here in this ring. There is a small gap of x. This distance is x, and this r is the radius of this charge here. Radius of this ring, and q is the total charge plus q is the total charge distributed uniformly on this. And if the given condition is this x is very small when compared to that of r, that means a small opening is there here. Now we need to find the electric field strength at the center of this ring here. When the small gap is there in the ring, it is not a complete ring. A small two ends are close to each other, but they are not in contact with each other. So a small gap x is there, such that x is very small when compared to that of r. Now that charge is distributed uniformly on this. Just we need to find electric field strength at the center of the ring. Find electric field strength at the center of the ring. So for that, you may consider this ring is made up of large number of elements. So then for this, for example, here if I consider one element here, then opposite element will be there here. So electric field produced by this element at this point will be in downward direction. And electric field due to this element at this point will be in upward direction, so that they cancel with each other. So like that for every element there will be opposite element will be there, so that the field at that point will be 0. But here now exactly opposite to this opening if you consider here. So here if I consider this opening a small element here opposite to that, exactly opposite to that of this. So actually we can mention like this. So that element now I can mention like this. So then if this element if I consider here, then this element here will produce electric field along this direction, D. But this element here there is no charge. If here also charge is there, if this also closed one, then this electric field, this element also produces electric field in this direction, so that net electric field at that point will be 0. But here this is opening is there, that means there is no charge here. And so only this field will be the unbalanced field here, and so that resultant electric field at that point is nothing but due to that small element only. So therefore I can write this electric field at that element is net electric field at that point is nothing but electric field due to this small element there. So which we can write it as k into dq by r square, electric field due to the small element, where dq is the charge present on this, which is identical element here. We need to cancel this identical element, so that here also this distance is x. That means we are going to use that point charge formula only. And so now this q value I can write this as q by 2 pi r, because here the thing is we are taking it as 2 pi r because this x is very small here. So when x is very small, you can almost assume that this total charge is distributed on this entire ring, you may consider. So that length I am taking it as 2 pi r. Actually we need to write 2 pi r minus x, but x is very small, so you can cancel it as 2 pi r into x by r square. So that finally I can write this as electric field is equal to q into x by 8 pi square epsilon naught r cube, we can write here. So this is the direction of this electric field. Magnitude of electric field, and the direction of electric field will be towards that gap. So wherever the gap is there, so the direction of this electric field will be towards that gap here. So that is the direction of this electric field. If there is such a small cutting is there in that ring, so you can cancel that as opposite element. Opposite element you may treat that as a point charge, and the point charge formula you can write here. Next, there will be some questions based on this graphs here. Just drawing the graph due to this electric field. So just I will give this graphs now. Try yourself. Otherwise, in the next class I will explain those graphs. So like here, let us consider this. This is our origin. So one charge is there here, another charge is there here. Both are like charges I am taking here. This is plus q and this is also plus q. Say both are separated by a distance of 2d, so that this distance is equal to d and this distance is also d. And let us take this as x-axis and this is our y-axis. So just here we need to draw the variation of this electric field when you are traveling along x-axis. So that means the first question here is two charges or fixed charges are there like this, both are like charges only, and both are identical charges you can draw. So the first question is draw the variation of electric field along x-axis. Next one is similarly draw the variation of electric field. So it is variation of electric field along y-axis. That means when you are traveling along x-axis, how the electric field is changing, and similarly when you are traveling along this y-axis, how the electric field is changing. So we need to represent those variations graphically there. So you can try yourself. Just remember, for the point charge we mentioned the graph like this. For the point charge we mentioned the graph like this. So here that indicates that the electric field due to this point charge is varying inversely proportional to the r square. That means when r value tends to 0, when r value is tending to 0, you can observe that electric field tends to infinity. The electric field at the site of this charge will be almost tends to infinity. And whereas when r value tends to infinity, the electric field value tends to 0. So it is a point you should remember regarding the point charge here. So now the similar concept now we can apply for this. Just here we need to cancel the electric field at any point due to both the charges, because two charges are there, identical charges are there, q and q, and so we need to cancel that electric field due to both the charges. So try this problem, and today solve those problems based on the principle of superposition. and complete those problems and try to draw this graph. Otherwise tomorrow I will explain this graph, and also solve the problems based on electric field due to a point charge from level 1 and level 2, and I will mention those question numbers in the WhatsApp group so you can solve those problems. Thank you.